A relay is an electrically operated switch. Many relays use an electromagnet to mechanically operate a switch, but other operating principles are also used, such as solid-state relays. Relays are used where it is necessary to control a circuit by a low-power signal, or where several circuits must be controlled by one signal. The first relays were used in long-distance telegraph circuits as amplifiers. They repeated the signal coming in from one circuit and retransmitted it on another circuit. Relays were used extensively in telephone exchanges and early computers to perform logical operations. A type of relay that can handle the high power required to directly control an electric motor or other loads is called a contactor. Solid-state relays control power circuits with no moving parts, instead using a semiconductor device to perform switching. Relays with calibrated operating characteristics and sometimes multiple operating coils are used to protect electrical circuits from overload or faults. In modern electric power systems, these functions are performed by digital instruments still called protective relays. Basic design and operation. A simple electromagnetic relay consists of a coil of wire wrapped around a soft iron core, an iron yoke which provides a low reluctance path for magnetic flux, a movable iron armature, and one or more sets of contacts. The armature is hinged to the yoke and mechanically linked to one or more sets of moving contacts. It is held in place by a spring so that when the relay is de-energized there is an air gap in the magnetic circuit. In this condition, one of the two sets of contacts in the relay pictured is closed, and the other set is open. Other relays may have more or fewer sets of contacts depending on their function. The relay in the picture also has a wire connecting the armature to the yoke. This ensures continuity of the circuit between the moving contacts on the armature, and the circuit track on the printed circuit board via the yoke, which is soldered to the PCB. When an electric current is passed through the coil, it generates a magnetic field that activates the armature, and the consequent movement of the movable contact, S, either makes or breaks a connection with a fixed contact. If the set of contacts was closed when the relay was de-energized, then the movement opens the contacts and breaks the connection, and vice versa if the contacts were open. When the current to the coil is switched off, the armature is returned by a force, approximately half as strong as the magnetic force, to its relaxed position. Usually this force is provided by a spring, but gravity is also used commonly in industrial motor starters. Most relays are manufactured to operate quickly. In a low-voltage application this reduces noise. In a high-voltage or current application it reduces arcing. When the coil is energized with direct current, a diode is often placed across the coil to dissipate the energy from the collapsing magnetic field at deactivation, which would otherwise generate a voltage spike dangerous to semiconductor circuit components. Some automotive relays include a diode inside the relay case. Alternatively, a contact protection network consisting of a capacitor and resistor in series may absorb the surge. If the coil is designed to be energized with alternating current, a small copper shading ring can be crimped to the end of the solenoid, creating a small out-of-phase current which increases the minimum pull on the armature during the AC cycle. A solid-state relay uses a thyristor or other solid-state switching device, activated by the control signal, to switch the controlled load, instead of a solenoid. An autocoupler coupled with a phototransistor, can be used to isolate control and controlled circuits. Types: Latching relay. A latching relay has two relaxed states. These are also called impulse, keep, or stay relays. When the current is switched off, the relay remains in its last state. This is achieved with a solenoid operating a ratchet and cam mechanism, or by having two opposing coils with an over-center spring or permanent magnet to hold the armature and contacts in position while the coil is relaxed, or with a remanent core. In the ratchet and cam example, the first pulse to the coil turns the relay on and the second pulse turns it off. In the two-coil example, a pulse to one coil turns the relay on and a pulse to the opposite coil turns the relay off. This type of relay has the advantage that one coil consumes power only for an instant, while it is being switched, and the relay contacts retain this setting across a power outage. A remnant core latching relay requires a current pulse of opposite polarity to make it change state. A stepping relay is a specialized kind of multi-way latching relay designed for early automatic telephone exchanges. An earth leakage circuit breaker includes a specialized latching relay. Very early computers often stored bits in a magnetically latching relay, such as VREAD or the later MANREAD in the 1ESS switch. Some early computers used ordinary relays as a kind of latch. They store bits in ordinary wire spring relays or reed relays by feeding an output wire back as an input, resulting in a feedback loop or sequential circuit. Such an electrically latching relay requires continuous power to maintain state, unlike magnetically latching relays or mechanically ratcheting relays. In computer memories, latching relays and other relays were replaced by delay line memory, which in turn was replaced by a series of ever faster and ever smaller memory technologies. Reed relay. A reed relay is a reed switch enclosed in a solenoid. The switch has a set of contacts inside an evacuated or inert gas-filled glass tube which protects the contacts against atmospheric corrosion. The contacts are made of magnetic material that makes them move under the influence of the field of the enclosing solenoid or an external magnet. Reed relays can switch faster than larger relays and require very little power from the control circuit. However, they have relatively low switching current and voltage ratings. Though rare, the reeds can become magnetized over time, which makes them stick on even when no current is present. Changing the orientation of the reeds with respect to the solenoid's magnetic field can resolve this problem. Sealed contacts with mercury-wetted contacts have longer operating lives and less contact chatter than any other kind of relay. Mercury-wetted relay. A mercury-wetted reed relay is a form of reed relay in which the contacts are wetted with mercury. Such relays are used to switch low-voltage signals where the mercury reduces the contact resistance and associated voltage drop, for low-current signals where surface contamination may make for a poor contact, or for high-speed applications where the mercury eliminates contact bounce. Mercury-wetted relays are position-sensitive and must be mounted vertically to work properly. Because of the toxicity and expense of liquid mercury, these relays are now rarely used. Mercury relay. A mercury relay is a relay that uses mercury as the switching element. They are used where contact erosion would be a problem for conventional relay contacts. Owing to environmental considerations about significant amount of mercury used in modern alternatives, they are now comparatively uncommon. Polarized relay. A polarized relay places the armature between the poles of a permanent magnet to increase sensitivity. Polarized relays were used in middle 20th century telephone exchanges to detect faint pulses and correct telegraphic distortion. The poles were on screws, so a technician could first adjust them for maximum sensitivity and then apply a bias spring to set the critical current that would operate the relay. External links, schematic diagram of a polarized relay used in a teletype machine. Machine tool relay. A machine tool relay is a type standardized for industrial control of machine tools, transfer machines, and other sequential control. They are characterized by a large number of contacts which are easily converted from normally open to normally closed status, easily replaceable coils, and a form factor that allows compactly installing many relays in a control panel. Although such relays once were the backbone of automation in such industries as automobile assembly, the programmable logic controller mostly displaced the machine tool relay from sequential control applications. A relay allows circuits to be switched by electrical equipment. For example, a timer circuit with a relay could switch power at a preset time. For many years relays were the standard method of controlling industrial electronic systems. A number of relays could be used together to carry out complex functions. The principle of relay logic is based on relays which energize and de-energize associated contacts. Relay logic is the predecessor of ladder logic, which is commonly used in programmable logic controllers. Ratchet relay. This is again a clapper-type relay which does not need continuous current through its coil to retain its operation. A ratchet holds the contacts closed after the coil is momentarily energized. A second impulse, in the same or a separate coil, releases the contacts. Coaxial relay. Where radio transmitters and receivers share a common antenna, often a coaxial relay is used as a tier relay, which switches the antenna from the receiver to the transmitter. This protects the receiver from the high power of the transmitter. Such relays are often used in transceivers which combine transmitter and receiver in one unit. The relay contacts are designed not to reflect any radio frequency power back toward the source, and to provide very high isolation between receiver and transmitter terminals. The characteristic impedance of the relay is matched to the transmission line impedance of the system, for example, 50 ohms. Contactor. A contactor is a heavy-duty relay used for switching electric motors and lighting loads, but contactors are not generally called relays. Continuous current ratings for common contactors range from 10 amps to several hundred amps. High current contacts are made with alloys containing silver. The unavoidable arcing causes the contacts to oxidize. However, silver oxide is still a good conductor. Contactors with overload protection devices are often used to start motors. Contactors can make loud sounds when they operate, so they may be unfit for use where noise is a chief concern. A contactor is an electrically controlled switch used for switching a power circuit, similar to a relay except with higher current ratings. A contactor is controlled by a circuit which is a much lower power level than the switched circuit. Contactors come in many forms with varying capacities and features. Unlike a circuit breaker, a contactor is not intended to interrupt a short circuit current. Contactors range from those having a breaking current of several amperes to thousands of amperes and 24 VDC to many kilovolts. A physical size of contactors ranges from a device small enough to pick up with one hand, to large devices approximately a meter on a side. Solid-state relay. A solid-state relay is a solid-state electronic component that provides a similar function to an electromechanical relay but does not have any moving components, increasing long-term reliability. Every solid-state device has a small voltage drop across it. This voltage drop limits the amount of current a given SSR can handle. The minimum voltage drop for such a relay is a function of the material used to make the device. Solid-state relays rated to handle as much as 1,200 amperes have become commercially available. Compared to electromagnetic relays, they may be falsely triggered by transients and in general may be susceptible to damage by extreme cosmic ray and EMP episodes. Solid-state contactor relay. A solid-state contactor is a heavy-duty solid-state relay, including the necessary heat sink, used where frequent on-off cycles are required, such as with electric heaters, small electric motors, and lighting loads. There are no moving parts to wear out and there is no contact bounce due to vibration. They are activated by AC control signals or DC control signals from programmable logic controller, PCs, transistor logic sources, or other microprocessor and microcontroller controls. Buchholz relay. A Buchholz relay is a safety device sensing the accumulation of gas in large oil-filled transformers, which will alarm on slow accumulation of gas or shut down the transformer if gas is produced rapidly in the transformer oil. Forced guided contacts relay. A forced guided contacts relay has relay contacts that are mechanically linked together, so that when the relay coil is energized or de-energized, all of the linked contacts move together. If one set of contacts in the relay becomes immobilized, no other contact of the same relay will be able to move. The function of forced guided contacts is to enable the safety circuit to check the status of the relay. Forced guided contacts are also known as positive guided contacts, captive contacts, locked contacts, mechanically linked contacts, or safety relays. Overload protection relay. Electric motors need overcurrent protection to prevent damage from overloading the motor, or to protect against short circuits in connecting cables or internal faults in the motor windings. The overload sensing devices are a form of heat-operated relay where a coil heats a bimetallic strip, or where a solder pot melts, releasing a spring to operate auxiliary contacts. These auxiliary contacts are in series with the coil. If the overload senses excess current in the load, the coil is de-energized. This thermal protection operates relatively slowly, allowing the motor to draw higher starting currents before the protection relay will trip. where the overload relay is exposed to the same environment as the motor, a useful though crude compensation for motor ambient temperature is provided. The other common overload protection system uses an electromagnet coil in series with the motor circuit that directly operates contacts. This is similar to a control relay but requires a rather high fault current to operate the contacts. To prevent short overcurrent spikes from causing nuisance, triggering the armature movement is damped with a dashpot. The thermal and magnetic overload detections are typically used together in a motor protection relay. Electronic overload protection relays measure motor current and can estimate motor winding temperature using a thermal model of the motor armature system that can be set to provide more accurate motor protection. Some motor protection relays include temperature detector inputs for direct measurement from a thermocouple or resistance thermometer sensor embedded in the winding. Vacuum relays, a sensitive relay having its contacts mounted in a highly evacuated glass housing, to permit handling radio frequency voltages as high as 20,000 volts without flashover between contacts even though contact spacing is but a few hundredths of an inch when open. Pole and throw. Since relays are switches, the terminology applied to switches is also applied to relays. A relay switch is one or more poles, each of whose contacts can be thrown by energizing the coil in one of three ways. Normally open contacts connect the circuit when the relay is activated. The circuit is disconnected when the relay is inactive. It is also called a form-A contact or make contact. NO contacts may also be distinguished as early make, or NOEM, which means that the contacts close before the button or switch is fully engaged. Normally closed contacts disconnect the circuit when the relay is activated. The circuit is connected when the relay is inactive. It is also called a Form B contact or break contact. NC contacts may also be distinguished as late break, or NCLB, which means that the contacts stay closed until the button or switch is fully disengaged. Changeover, or double throw, contacts control two circuits, one normally open contact and one normally closed contact with a common terminal. It is also called a Form C contact or transfer contact. If this type of contact utilizes a make-before-break functionality, then it is called a Form D contact. The following designations are commonly encountered: SPST, a Euro single-pole single-throw. These have two terminals which can be connected or disconnected. Including two for the coil, such a relay has four terminals in total. It is ambiguous whether the pole is normally open or normally closed. The terminology SPNO and SPNC is sometimes used to resolve the ambiguity. SPDT, a Euro single-pole double-throw. A common terminal connects to either of two others. Including two for the coil, such a relay has five terminals in total. DPST, a Euro double-pole single-throw. These have two pairs of terminals. Equivalent to two SPST switches or relays actuated by a single coil. Including two for the coil, such a relay has six terminals in total. The poles may be Form A or Form B. DPDT, a Euro double-pole double-throw. These have two rows of changeover terminals. Equivalent to two SPDT switches or relays actuated by a single coil. Such a relay has 8 terminals, including the coil. The S, or D may be replaced with a number, indicating multiple switches connected to a single actuator. For example, 4PDT indicates a 4-pole double-throw relay. EN 50005 are among applicable standards for relay terminal numbering. A typical EN 50005 compliant SPDT relay's terminals would be numbered 11, 12, 14, A1 and A2 for the C, NC, NO, and coil connections, respectively. DIN 72552 defines contact numbers and relays for automotive use. 85 equals relay coil, 86 equals relay coil plus, 87 equals common contact, 87 areas equals normally closed contact, 87B equals normally open contact. Applications: relays are used for amplifying a digital signal, switching a large amount of power with a small operating power. Some special cases are, a telegraph relay, repeating a weak signal received at the end of a long wire, controlling a high-voltage circuit with a low-voltage signal, as in some types of modems or audio amplifiers, controlling a high-current circuit with a low-current signal, as in the starter solenoid of an automobile. Detecting and isolating faults on transmission and distribution lines by opening and closing circuit breakers. Isolating the controlling circuit from the controlled circuit when the two are at different potentials, for example when controlling a mains-powered device from a low-voltage switch. The latter is often applied to control office lighting as the low-voltage wires are easily installed in partitions, which may be often moved as needs change. They may also be controlled by room occupancy detectors to conserve energy, logic functions. For example, the Boolean AND function is realized by connecting normally open relay contacts in series, the OR function by connecting normally open contacts in parallel. The changeover or Form C contacts perform the XOR function. Similar functions for NAND and NOR are accomplished using normally closed contacts. The ladder programming language is often used for designing relay logic networks. The application of Boolean algebra to relay circuit design was formalized by Claude Shannon in a symbolic analysis of relay and switching circuits, early computing. Before vacuum tubes and transistors, relays were used as logical elements and digital computers. See electromechanical computers such as the ARRA, Harvard Mark II, ZOO Z2, and ZOO Z3. Safety-critical logic. Because relays are much more resistant than semiconductors to nuclear radiation, they are widely used in safety-critical logic, such as the control panels of radioactive waste handling machinery. Time delay functions. Relays can be modified to delay opening or delay closing a set of contacts. A very short delay would use a copper disc between the armature and moving blade assembly. Current flowing in the disc maintains magnetic field for a short time, lengthening release time. For a slightly longer delay, a dash pot is used. A dash pot is a piston filled with fluid that is allowed to escape slowly. The time period can be varied by increasing or decreasing the flow rate. For longer time periods, a mechanical clockwork timer is installed. Vehicle battery isolation. A 12V relay is often used to isolate any second battery in cars, 4WDs, RVs and boats. Switching to a standby power supply. Relay application considerations. Selection of an appropriate relay for a particular application requires evaluation of many different factors, number and type of contacts normally open, normally closed, contact sequence make before break, or break before make. For example, the old-style telephone exchanges required make before break so that the connection didn't get dropped while dialing the number. Rating of contacts small relays switch a few amperes, large contactors are rated for up to 3000 amperes, alternating or direct current. Voltage rating of contacts typical control relays rated 300 VAC or 600 VAC, automotive types to 50 VDC, special high-voltage relays to about 15,000 V, operating lifetime, useful life, the number of times the relay can be expected to operate reliably. There is both a mechanical life and a contact life. The contact life is naturally affected by the kind of load being switched. Switching while wet causes undesired arcing between the contacts, eventually leading to contacts that well shut or contacts that fail due to a build-up of contact surface damage caused by the destructive arc energy. Coil voltage machine tool relays usually 24 VDC, 120 or 250 VAC, relays for switchgear may have 125 V or 250 VDC coils. Sensitive relays operate on a few milliamperes. Coil current, including minimum current required to operate reliably and minimum current to hold. Also effects of power dissipation on coil temperature at various duty cycles. Package enclosure open, touch safe, double voltage for isolation between circuits, explosion proof, outdoor, oil and splash resistant, washable for printed circuit board assembly, operating environment, minimum and maximum operating temperatures and other environmental considerations such as effects of humidity and salt. Assembly Some relays feature a sticker that keeps the enclosure sealed to allow PCB post-soldering cleaning, which is removed once assembly is complete. Mounting a Euro sockets, plug board, rail mount, panel mount, through panel mount, enclosure for mounting on walls or equipment, switching timer Euro, where high speed is required, dry contacts Euro, when switching very low level signals. Special contact materials may be needed such as gold-plated contacts, contact protection Euro suppress arcing in very inductive circuits, coil protection Euro suppress the surge voltage produced when switching the coil current, isolation between coil contacts, aerospace or radiation-resistant testing, special quality assurance, expected mechanical loads due to acceleration Euro some relays used in aerospace applications are designed to function in shock loads of 50 G or more. Size: smaller relays often resist mechanical vibration and shock better than larger relays, because of the lower inertia of the moving parts and the higher natural frequencies of smaller parts. Larger relays often handle higher voltage and current than smaller relays. Accessories such as timers, auxiliary contacts, pilot lamps, and test buttons, regulatory approvals, stray magnetic linkage between coils of adjacent relays on a printed circuit board. There are many considerations involved in the correct selection of a control relay for a particular application. These considerations include factors such as speed of operation, sensitivity, and hysteresis. Although typical control relays operate in the 5 milliseconds to 20 milliseconds range, relays with switching speeds as fast as 100 S are available. Reed relays which are actuated by low currents and switch fast are suitable for controlling small currents. As for any switch, the current through the relay contacts must not exceed a certain value to avoid damage. In the particular case of high inductance circuits such as motors, other issues must be addressed. When an inductance is connected to a power source, an input surge current or electromotor starting current larger than the steady current exists. When the circuit is broken, the current cannot change instantaneously, which creates a potentially damaging spark across the separating contacts. Consequently, for relays which may be used to control inductive loads, we must specify the maximum current that may flow through the relay contacts when it actuates, the make rating, the continuous rating, and the break rating. The make rating may be several times larger than the continuous rating, which is itself larger than the break rating. Derating factors: control relays should not be operated above rated temperature because of resulting increased degradation and fatigue. Common practice is to derate 20 degrees Celsius from the maximum rated temperature limit. Relays operating at rated load are also affected by their environment. Oil vapors may greatly decrease the contact tip life, and dust or dirt may cause the tips to burn before their normal life expectancy. Control relay life cycle varies from 50,000 to over 1 million cycles depending on the electrical loads of the contacts, duty cycle, application, and the extent to which the relay is derated. When a control relay is operating at its derated value, it is controlling a lower value of current than its maximum make and break ratings. This is often done to extend the operating life of the control relay. The table lists the relay derating factors for typical industrial control applications. Undesired arcing. Switching while wet causes undesired arcing between the contacts, eventually leading to contacts that well shut or contacts that fail due to a build-up of contact surface damage caused by the destructive arc energy. Inside the 1ESS switch matrix switch and certain other high-reliability designs, the reed switches are always switched dry to avoid that problem, leading to much longer contact life. Without adequate contact protection, the occurrence of electric current arcing causes significant degradation of the contacts in relays, which suffer significant and visible damage. Every time a relay transitions either from a closed to an open state or from an open to a closed state, under load, an electrical arc can occur between the two contact points of the relay. The break arc is typically more energetic and thus more destructive. The heat energy contained in the resulting electrical arc is very high, causing the metal on the contact surfaces to melt, cool and migrate with the current. The extremely high temperature of the arc cracks the surrounding gas molecules, creating ozone, carbon monoxide, and other compounds. The arc energy slowly destroys the contact metal, causing some material to escape into the air is fine particulate matter. This very activity causes the material in the contacts to degrade quickly, resulting in device failure. This contact degradation drastically limits the overall life of a relay to a range of about 10,000 to 100,000 operations, a level far below the mechanical life of the same device, which can be in excess of 20 million operations. Protective relays. For protection of electrical apparatus and transmission lines, electromechanical relays with accurate operating characteristics were used to detect overload, short circuits, and other faults. While many such relays remain in use, digital devices now provide equivalent protective functions. Railway signaling. Railway signaling relays are very big and cumbersome considering the mostly small voltages and currents that they switch. Contacts are widely spaced to prevent dangerous flashovers and short circuits over a lifetime that may exceed 50 years. BR930 series plug-in relays are widely used on railways following British practice. These are 120 ohm high, 180 ohm deep and 56 ohm wide and weigh about 1400 Ag, and can have up to 16 separate contacts, for example, 12 make and 4 break contacts. The branch Q-type relay are available in a number of different configurations, QN1 neutral, QL1 latched, see above, QNA1 AC immune, QBA1 biased AC immune, see above, QNN1 twin neutral 2x4-4 or 2x6-2, QBCA1 contactor for high current applications such as point motors. QTDX, timer, since rail signal circuits must be highly reliable, special techniques are used to detect and prevent failures in the relay system. To protect against false feeds, double switching relay contacts are often used on both the positive and negative side of a circuit, so that 2 false feeds are needed to cause a false signal. Not all relay circuits can be proved, so there is reliance on construction features such as carbon-to-silver contacts to resist lightning-induced contact welding and to provide AC immunity. Opto-isolators are also used in some instances with railway signaling, especially where only a single contact is to be switched. Signaling relays, typical circuits, drawing symbols, abbreviations and nomenclature, etc. come in a number of schools, including United States, France, Germany, United Kingdom. American shelf-type signaling relays are the origin of the 19-inch rack. History. The American scientist Joseph Henry invented a relay in 1835 in order to improve his version of the electrical telegraph, developed earlier in 1831. It is claimed that the English inventor Edward Davies certainly invented the electric relay in his electric telegraph c. 1835. A simple device, which we now call a relay, was included in the original 1840 telegraph patent of Samuel Morse. The mechanism described acted as a digital amplifier, repeating the telegraph signal, and thus allowing signals to be propagated as far as desired. This overcame the problem of limited range of earlier telegraphy schemes. The word relay appears in the context of electromagnetic operations from 1860. See also, contactor, digital protective relay, dry contact, race condition, stepping switch, a kind of multi-position relay, wire spring relay. References. External links, electromagnetic relays and solid-state relays, general technical descriptions, functions, shutdown behavior and design features, the electromechanical relay, information about relays and the latching relay circuit, Harry Porter's relay computer, a computer made out of relays. Relay Computer 2, by John Stanley. Interfacing relay to microcontroller. Relays technical right, http, relays TECOM PDF COV4BG5 PDF.